Have you ever wondered how much fuel that the Enterprise, the Millennium Falcon, or the Battlestar Galactica uses when it travels faster than light? Stay tuned and find out. I'll explain how we can calculate it. All right, in this episode, I'm going to go through the derivation of how to calculate the rocket equation, the relativistic rocket equation, and what I call the Tachyon rocket equation, which will describe how much fuel a spacecraft will use when it's traveling from lower than light speeds at the speed of light, and then of course to faster than light travel. All propulsion systems that we know of right now use mass ejection. In other words, we have to apply some kind of momentum exchange between the exhaust and the spacecraft to propel it forward. Now, momentum energy exchange is simply taking a certain quantity of energy and applying it to a mass, such as a spacecraft, and then propelling it forward at some sort of speed. So here in this picture, we have our little energy power plant. This could be nuclear power, for example. We apply it to our spacecraft, and then it produces momentum that pushes the spacecraft at some given velocity. Now, to understand the rocket equation, we have to define a few variables. So here I have my spacecraft piloted by this little astronaut gal here, and she is ejecting some mass coming out the back. And of course, we have Einstein, and he's attached to that mass as it's being propelled backwards. So we have to define a few labels. First, we need to know what is the mass of the spacecraft, what is its velocity. Then we also have the reaction mass, propellant mass that we're pushing out the back. We also need to know the reaction mass velocity as it's leaving the spacecraft, and then we need to know the difference what the exhaust velocity is, which is the difference between how fast the spacecraft is moving forward and the reaction mass velocity. Now, out of all these variables, the only two that are constant would be the reaction mass and the exhaust mass. We're going to assume that those don't change, but that the mass of the spacecraft obviously will vary depending on how much fuel it's burning. Its mass or weight will decrease as fuel is being used. The same can be said of the reaction mass. Now, the mass of a spacecraft is going to be composed of the rocket's empty mass without any fuel, cargo, or people put on board. We then have the mass of the crew and passengers. We have the fuel mass, or how much fuel we're going to load onto that spacecraft. And then finally, we're going to put on a payload mass, which could be equipment, food stores, a satellite, anything else that we wish to carry on the spacecraft. Now, we simply need to sum all these up. So the total mass of a spacecraft at launch is going to be its empty weight without any fuel or people on board, plus the crew, and then we also add on the cargo, and also the amount of fuel that is going to be put on board. Together, this is the total mass of a launch vehicle at takeoff. From conservation of momentum, we will look at the mass and its velocity before, and then we'll look at how much mass and what its velocity is after. And this exchange of momentum is a result of the conservation, is known as the conservation of momentum. The conservation of momentum is a law that tells us how much momentum we had before a reaction to how much mass and velocity we have after a reaction. So we can think of it as what is our speed at time zero, and then at some later time we can say what is its mass and speed at some later time. Now, an additional law is called the conservation of energy, and from that we need to determine how much energy the rocket had before before it turns on its engine, and then we need to know how much energy is expended at some later time. and between the conservation of energy and the conservation of momentum, we can derive the rocket equation. A third piece of information that we need is how velocities are added together. We have the velocity of the reaction mass, we have the exhaust velocity, as well as the velocity of the spacecraft. So we need to be able to transform, to make a calculation, we need to transform our variables from one reference frame to another reference frame. A Russian scientist named Tsiolkovsky developed the rocket equation. And by taking these three pieces of information, the conservation of momentum, the conservation of energy, and coordinate changes for our velocity, he was able to derive the classical rocket equation. So here, we simply take the momentum, we plug in the values for energy, we also plug in the transformation for velocity, and we can, after some algebra manipulation, we then get a form of the equation that we can integrate. Once we integrate it, we have the final equation, which simply states that we have the final mass, which is equal to the initial mass, times the exponential of the change in velocity divided by the exhaust velocity. So essentially what this tells us is when we turn our rocket engine on and the exhaust is coming out the back at a constant velocity, and we shut it off at some time later, it will tell us what the initial mass is and what our final mass is. So it gives us a measure of how much fuel has been consumed by our rocket engine. Hi, I just want to take a few minutes and tell you thank you for watching my video. I put a lot of time and effort into making these, and if you could hit that like button and subscribe button and warp me to the top of the list, more people will be able to enjoy these. So make sure and hit that like button and subscribe button, and let's continue watching the rest of the video. Thank you. The classical rocket equation was originally derived for velocities that are less than the speed of light. So what will the equation look like when we transition to relativistic velocities, or velocities that are approaching near light speeds? So once again, let's consider our rocket. We have our female astronaut on a rocket, and it's expelling some mass, it's ejecting mass and through exhaust, and this could be a nuclear reaction or some sort of chemical reaction or some exotic reaction that we haven't yet discovered. So essentially we're going to follow the same steps, only we're going to need some more information. So the first thing we'll need is the obviously the mass of the rocket, the velocity of the spacecraft, the reaction propellant of the exhaust coming out the back, and also the exhaust velocity with respect to the spacecraft. In addition to all these, we also need to take into account the relativistic effects, and these are these two parameters are derived from the Lorentz factor from special relativity. And I have some other videos that go into it in depth, and if you want to watch them, they're right up here. Check out this video and I'll explain more about relativistic effects for velocities below the speed of light as well as velocities that are above the speed of light. So now we still apply the conservation of relativistic momentum, only this time we're going to include our two Lorentz factors. One will be for the spacecraft, the other one will be for the relativistic effects of the exhaust and the plume that comes out of the rocket engine. Next, we'll apply the conservation of relativistic energy. In this case, it's identical to the classical result, except for we need to include relativistic effects through the Lorentz gamma factors. Now we're going to have one for the spacecraft and another one for the exhaust that's coming out of the engine. The final piece of information we need is how to add velocities together for relativistic situations. In this case, it's quite different from our previous one. We have to take into account the relativistic effects, And you can see here in this equation that it comes out, it's a little bit more complicated. As the rocket ship zooms to the right and the plume zooms to the left, we need to be able to transform information from one reference frame back to another, and that in order for us to make calculations. The final form of our relativistic rocket equation looks like this. It's quite simple. We just simply have the exhaust velocity minus the velocity of the spacecraft, and that's divided by the product of the two of them. Now, just as a review, in my previous video, I developed a Lorentz gamma factor that not only took into account relativistic effects below the speed of light, but it also takes into account velocities at faster than the speed of light. So as a brief review, I'm just going to go through it for this particular video that I'm doing now. So a generalized Lorentz gamma factor can be written where we take the classical Lorentz factor and we multiply it by the square root of a transition function. Now the transition function allows us to smoothly transition from less than light speeds to faster than light speeds. The transition function is simply a hyperbolic function that transitions from a +1 through to a -1. And we can break this transition function down into three regions. When we're below the speed of light, the transition function is approximately equal to 1. When it's nearly equal the speed of light, we get essentially a constant value. And then when it's faster than the speed of light, it becomes a -1. So here I've plotted the transition function, and you can see when the velocity is less than the speed of light, we get a value of 1. When it's greater than the speed of light, we get a -1. And when it's nearly equal to the speed of light, we get a slope. Now this slope of the line is determined by the temporal coefficient. And basically it's a description of how wide or how thick the light barrier is that we're passing through. It's similar to the to air density that creates a shock wave around an aircraft. It tells us how thick that shock wave can be. And in this case, the temporal coefficient tells us how thick the light barrier could possibly be. And I described that in previous videos, so I encourage you to go back and check out videos 1 through 4. They go into a lot more detail on what that exactly is. Now, to simplify our calculations, we're going to assume that there's no velocity in the x direction, no velocity in the y direction, and we have just one-dimensional motion along the z-axis. So in other words, we're just going to consider a starship like the Enterprise and the Millennium Falcon just traveling along in one dimension. So setting the velocities to 0 for the x and y, and we'll just write the velocity in the z direction and label it simply as z. Now we're going to describe the warp factor as simply the ratio of velocity to the speed of light. The transition function has two points that we can use to validate when we're below the speed of light and between crossing the light barrier and when we're traveling faster than the speed of light. And the difference between these 2 points is roughly the thickness of what the light barrier possibly could be. Solve for the turning point, and I labeled the first one A, and it's simply the square root minus 1 over the transition function. Likewise, for our second turning point, I labeled that B, and it is simply the square root of 1 plus the inverse of the temporal coefficient. Now, what this enables us to do is we can now write 3 forms of the Lorentz gamma factor. So I have here a generalized form, which is the transition function times the classical Einstein Lorentz factor. When we are below the speed of light, the transition function is equal to 1, and we get the classical result as expected. When we're approximately equal to the speed of light, the Lorentz factor is roughly a constant that depends on the temporal coefficient. And when we're faster than the speed of light, we get what I call the tachyon Lorenz gamma factor, and it simply states that nothing can travel slower than the speed of light, whereas the classical Lorenz factor says that nothing can travel faster than the speed of light. Now, for the purposes of our calculations, we have to designate a Lorenz gamma factor 1 for the spacecraft and another one for the amount for mass that's being ejected out by the engine. So here in this picture, I have a rocket ship being pushed along, and it's got flames coming out the back. So we'll have one Lorenz gamma factor to describe relativistic and tachyon effects for the spacecraft itself. Then we will have another one, and it's this little fireball that represents the mass that we're ejecting out the back. So what this allows us to say is that we can have relativistic effects for the spacecraft traveling below at the speed of light and faster than the speed of light, as well as matter that we're using as fuel that could be below the speed of light, at the speed of light, or faster than the speed of light. Finally, taking all three pieces of this information, we take our energy equation, we take our velocity transformations, and we plug that into the momentum, and we step through the algebra to finally derive at a generalized rocket equation that will describe lower than light speed rockets, as well as faster than light speed and light speed rocket equations. Now, integrating the mass term, we get essentially a natural log of the final mass over the initial mass. Integrating the volume term, we get essentially a natural log, which consists of the ratio of velocity, 1 plus the velocity over 1 minus the velocity, or if you want to think of it this way, 1 plus the warp factor divided by 1 minus the warp factor, and that is all to the power of whatever exhaust velocity is propelling the spacecraft forward. Integrating the transition function, we find that it becomes the natural log of the square root of the transition function itself. Now, plugging these all together, we can see we have the natural log of the mass terms on the right, which is equal to the natural log of the velocity terms, plus the natural log of our transition function. Then all we need to do is we can manipulate this by multiply through by an exponential, and we end up with a form that looks something like this. This form of the equation isn't exactly useful, so what we can do is we can multiply the top and bottom by the transition function, which has the ratio of the speed of light to the exhaust velocity. And what this will do is allow us to pull the transition function into the term on the right, and it gives us a very nice clean equation to work with. So this is what, after some algebra, this is what you come up with. Now the first term there we can simply drop, because it turns out that it's approximately equal to 1. It does vary a little bit once you are near the speed of light, but the effect is negligible, especially if the temporal coefficient is really large. So we will just drop that from our equation and consider it negligible. And voila! We have rearranged the rocket equation into our final form, and I'm so excited that I was able to do this, because this is very useful in terms of being able to engineer and design rocketry, and possibly figure out how we can develop an engine and a rocket craft system that can travel faster than the speed of light. All right, let's take the limit of a spacecraft that's traveling less than the speed of light, or a sublight speed. So we'll approximate our transition function to be equal to 1, and our warp factor is less than 1, and we get back the relativistic form of a rocket equation. Now, if you want to see the full derivation, there are lots of research papers on this. Particularly a good one is on Wikipedia. I'll leave the link in the description if you want to look it up yourself. As a reminder, we had these two transition turning points, one at A and one at B. And let's discuss what happens once we're in between A and B. So in other words, the spacecraft is transitioning light barrier. We now can write an equation that describes the fuel used by spacecraft when it's traveling near light speeds, okay? And so in this limit, we get a mass fraction that is equal to the temporal coefficient times a velocity term, which we can manipulate and simplify down. Now remember that this velocity is in a very tight window. It's only in between the point A and point B, as I previously described. This is the exciting part. We can now come up with a Tachyon rocket equation, an equation that is the mirror image of the relativistic rocket equation. And what this describes is the fuel mass usage of a rocket when it's traveling at faster than light speeds. So in this case, we take the limit of the step function, and it is roughly equal to -1 for velocities that are much greater than the speed of light, or much greater than a warp factor of 1. And you can see that it's nearly identical as a relativistic form, except that that bottom term has switched places. Instead of it being 1 minus the warp factor, it's now warp factor -1. Okay, so here are our three rocket equations. The first one is the relativistic form. The second one is for a spacecraft traveling near light speeds or crossing the light barrier. And the last one is the Tachyon relativistic equation for a spacecraft that's traveling faster than the speed of light. All three of these can be utilized to calculate how much fuel a spacecraft is using in each of these three cases. And then all we simply need to do is calculate how much fuel it's used below the speed of light, how much fuel it used near the speed of light, and then how much fuel it used above the speed of light, and then add them all together, and that will give us our total fuel usage for a spacecraft that's traveling faster than the speed of light. So this would describe something like the Enterprise traveling at warp 4, or warp 5, or the Millennium Falcon making the Kessel run in 12 parsecs. Hey, thanks for watching my video. Don't forget to hit the like button and the subscribe button, and comment on what you think of my theories below. The two biggest factors that determine that affect these rocket equations are, one, the temporal coefficient. The temporal coefficient determines how easily a particle can transition the light barrier, which in turn will also determine the exhaust velocity. So in this scenario, we are going to assume that we have a rocket engine and that we have some sort of warp field, some kind of mechanism that allows us to take particles and turn them into tachyons. So a tachyon is simply a particle that travels faster than the speed of light. So here in this picture, let's imagine we have some sort of engine that is ejecting mass out the back. We're applying some kind of warp field to it, and this warp field allows us to change the temporal coefficient. If we're able to manipulate this temporal coefficient, it'll make it easier for us to get particles to accelerate up faster than the speed of light. So essentially, we could use the basic components of, say, a nuclear powered rocket. We apply some sort of, call it a warp core or warp field. And at this point, I'm not going to speculate quite yet on how this could be done. That'll be for another video. But let's say we have that technology and we're generating tachyon particles. And essentially, we're going to say that we're generating a tachyon thrust. So the thrust coming out the back are particles that are traveling at faster than light speed. So this is essentially a tachyon rocket engine. So why would tachyon particles be advantageous to have? So look, I made a graph here, and if you look at this graph, I plotted the relativistic rocket equation alongside the tachyon rocket equation. And what you'll see here is these red lines represent exhaust velocities for particles that are traveling less than the speed of light. Now, when particles travel less than the speed of light, we call them bradyons. So bradyons are currently particles that we're already working with. So when you take, for example, kerosene and oxygen, which is used in a lot of rockets, they combine together and they are expelled out the back, and they have a certain velocity that they're achieved, but they're traveling at less than the speed of light. So we can see here that it takes a lot of fuel mass to produce the thrust we needed to travel near the speed of light. Next, you'll see this thin pink line, and the thin pink line would be a system that uses a photon rocket. So you could imagine some sort of antimatter reaction that generates huge amounts of photon and pushes them out the back. And the fuel mass usage for that rocket is quite a bit less than for a rocket that uses bradyon particles or conventional particles that we're using right now. Then finally, we can consider and say, what if we had an exotic form of matter? What if we had an exhaust velocity composed of tachyons? That's represented by the blue line. And you can see that as the tachyon velocity increases, as we go from, I have here in this picture, from a warp factor of 2 to a warp factor of 6, meaning that the exhaust is traveling 2 times the speed of light, 6 times the speed of light, 20 times the speed of light, our fuel massage goes down. And this is advantageous because that means that we're using our fuel mass much more efficiently. And this will provide a way for us to travel intergalactically from one star system to another, because it requires less mass and we're applying more energy coming out the back. Now, there are a lot of few quirky things that happen with tachyons when they travel at faster than light speeds. And check out my other videos because I go into a lot more detail. I don't have time to go into it in this one, but let's just go with the idea that tachyon particles can be created and can be producing thrust to power a spaceship. You're Han Solo and you just climb on board the Millennium Falcon, and you need to calculate how much fuel you're going to need going from point A to point B. So you climb on board and you're going to piece this together. We can use the equations that we've developed so far to come up with a mission profile for such a journey. So in this, our spacecraft departs, in this case Earth. We can apply sublight fuel equations up till it hits the light barrier, and then we can apply the transition equations for nearly light speeds, and then finally we can say that we're going to travel up to a cruise speed. Let's say our cruise speed is warp 10, and then we're going to stay at warp 10 until we have to decelerate, and then we reverse the whole process over. So the next few calculations I'm going to go through, we're just going to calculate the fuel usage going from a velocity of 0 up to warp 1 or the speed of light, and then finally to a cruise speed of, say, warp 10. And as a reminder, we're going to make our calculation based on these transition points that I was talking about earlier. When we're below the speed of light, we'll use that one. When we're in between point A and B, we'll use our light-like one. And when we're above B, we'll use the tachyon version. In this diagram, I've laid out how we're going to define all this. So we have points 1 and 2, which define the spacecraft traveling below the speed of, starting from rest up to the speed of light. Then points 3 and 4, which will transition the speed of light. And finally, points 5 and 6, as it goes faster than the speed of light. So a couple important parameters. We're going to say, what is its initial mass? What is the mass of the rocket just before it launches? The second one is we're going to have mass A at point A, or point 2 and 3, if you want to think about that way. And then we have mass B at point B, which is coincident with points 4 and 5. And I call this the transitional mass, or the mass, the fuel mass needed to transition the light barrier. And then finally, we're going to have a final mass once we reach our cruise speed of warp 10 in this example. So it's real easy to calculate what our fuel masses will be. So between points 1 and 2, we simply plug in what our velocity parameters are. So we'll say that our velocity, we're leaving the Cape Canaveral, the velocity sitting on the ground is 0. And then it's going to travel up to our first transition point, which will be the warp factor at point A. So I called it warp factor A in this case, or beta A. And then we're going to have the fuel mass transitioning the light barrier. So it's going to be the fuel mass from the warp point, or the turning point A minus the turning point B. And the same goes for when we're traveling faster than light speed. So we'll start from point B up to our final velocity. So for our first calculation, we write down this mass the difference in masses here, and we can see we get an initial mass at velocity 0, and we have some final mass usage at point A, and this is the form of the equation we get, which is simply 1 minus our velocity terms at the turning point A. Next, we'll need to make some calculations for our transition mass between A and B. And here, I'll just put the equations out here. I'm not going to go through and describe them, but essentially we have 2 points for velocity A and for velocity B, and from that we can get an equation that describes our mass usage as we're transitioning or nearly the speed of light. And finally, we have the fuel mass above the light barrier, and that would be calculating it from point 5 to point 6. And we simply take the difference from our turning point or velocity point at B, and we subtract that from our final velocity, which would, in this case, is going to be the warp factor of 10. In summary, here are our fuel mass equations. The first one is just describing the amount of fuel we use going from 1 to 2. Second one describing our fuel usage going from 3 to 4. And the last one is our fuel usage going from 5 to 6. And just recall that our transition points, we have our warp factor at A, which is 1 minus 1 over our temporal coefficient, and warp factor at B, which is 1 plus 1 over the temporal coefficient. And that describes the transition across the light barrier. At the boundary points of A and B, we can equate this to the change in mass going from 1 to 2, and at B, we can relate that to the change in mass going from 3 to 4. So this allows us to set our boundary conditions at A and B for each of our sections. All right, this is exciting. In this graph, I plotted how much fuel we're going to use. The red describes how much fuel the spacecraft uses up to point A, and then from point B, or from point A to point B, that's described by the blue line. That tells us how much fuel we use transitioning the light barrier, and then finally from point B to our warp factor of 10 describes how much fuel we're using at faster than light speeds. Now notice something, this is incredible here. We use most of the amount of fuel just reaching the light barrier. We use the least amount of fuel crossing the light barrier and when we're traveling at faster than light speeds. So our fuel usage drops dramatically at faster than light speed, or at tachyon speed. It just takes a little bit of fuel to make us go faster. Now recall that tachyons are required to lose energy in order to go faster. So it makes sense that just a little bit of change in our output can increase our speed fourfold, for example. Let's make a simplified fuel mass calculation. In this case, we're going to use 100 units as our initial mass. Just for the sake of discussion, I'm just going to call it 100 units, but you know, it could be a couple tons or whatever you want, but just for the purposes of this video and helping us understand it, we're just going to call it 100 units. We'll also are going to say that our engine is designed to have an exhaust velocity that's 10 times the speed of light. So in other words, we have an engine that's able to eject matter out the back as tachyons, and these tachyon particles have an average velocity of warp factor 10. We'll also set our initial velocity of the spacecraft to be 0 to aid in our calculation, and we'll also say that our warp field that we're using to manipulate the engine, the coefficient is approximately 2. In reality, the warp coefficient is of the order of like 10 to the 56, but it really clutters up the graphs when you go to a value that large. So we're just going to use a sigma of 2 just to illustrate the mathematics that's involved. Going back to our fuel mass graph again, we can say that we have this black area, and we can see that the mass going from 1 to 2 is where we will consume most of the fuel mass. Transitioning the light barrier will be is labeled by the delta M of 3 to 4, and the last part is our fuel usage for tachyon speed, which goes from 5 to 6. So here are some calculations that I made. Now these calculations are total amount of units used. So we can see up to point A, or the first region going from 1 to 2, we used 8.436 units. After we crossed the light barrier, we had used 8.638 units. And then by the time we reached a warp factor of 10, it was 9.488 units. So the total amount of fuel that we have used is 9.48, or roughly 9.5. Now, if we divide this by 100, we get a mass fraction, or how much, what fraction of our spacecraft was fuel versus the payload and the empty weight of the spacecraft. And we can see that it comes out to be 0.095%, which it would be incredible to achieve, although it's probably not realistic. But this is just an example, just to give a flavor of how we can apply these equations to a possible situation if we for a spacecraft that's traveling at faster than light speeds. Now, I also made some calculations that show us how much we're using at each segment. So the first one doesn't really change. We used 8.436 units. While transitioning the light barrier, we used only 0.198, which is a very small fraction. And then when we're at faster than light speeds up to warp 10, we used approximately 0.85 units. So it's the same calculation, but just I broke it down a little bit different. The first graph was just total amount of fuel used. This one broke it down by each segment. I hope you enjoyed this presentation I gave. If you found value in it, I would really appreciate it if you hit the like and subscribe button. Also, give me any comments on possibly where I made a mistake in the calculation, or your thoughts on faster than light travel. I also have a book available on Amazon where I go into a lot more detail and show the gory math and everything. I'll leave a link for that in the description below. So please hit that like button and hit that subscribe button. That'll help promote my videos and get them out there. So thank you very much for watching.